In his investigation of planets, Newton himself also develops a brand new type of telescope. While Galileo developed one working off of lenses, Newton developed one that was working off of mirrors that allowed for a lot more light and a lot more detail of the planets and moons in our solar system. With the greater amount of accuracy in observations, he was able to unravel more details about how the universe works. Using his improved data and his laws of motion, he was able to develop then his law of gravity. He starts with the first and second law. The first one showing on how, since the objects are changing direction and speed, there must be an external force acting on the system. And then by using his second law saying the net force on an object or system must equal its mass times acceleration. So the net force acting on any planet must equal the mass of that planet times that planet's acceleration. But that acceleration is centripetal. So the net force on any planet is equal to the mass of that planet times its centripetal acceleration. While there are all of these small objects all around in the universe, the predominant thing that everything is orbiting around is the sun. So we're going to have to estimate that the net force on the planet is really just the force of gravity from the sun. Please notice it is an estimation, but that's the best we can work with at this time. So this means that the force of gravity from the sun only is approximately equal to the mass of the planet that we're observing times that planet's centripetal acceleration. And the properties of the sun are what's causing that acceleration, because the mass of the planet does not play a role with that, since it is self-canceling out. Newton then was able to compare the distance that the planets are from the sun to their personal centripetal acceleration around the sun, and saw that there was an inverse squared relationship between the distance a planet is from the sun and its acceleration around the sun. This means if a planet was 5 times farther away than another planet, its acceleration was 25 times smaller than the planet that was closer. And since the net force acting on the planet, which is essentially the force of gravity from the sun, is equal to the planet's mass times its acceleration, then the force due to gravity from the sun on the planet must also follow the same inverse squared relationship. So again, if I was 10 times the distance away from the sun, the force of gravity on me would be 100th of what it was before. But other than distance, what other factors would affect gravity? This is now where Newton had to take a look at the individual planets and their moons. He can't just come up with everything from just the sun and the planets, because there's only one factor that's changing between the sun and the planets that's of consequence, and that's the distance. So now by looking at the individual planets, all with their individual masses, and see how they affect their moons, you can come up with a better understanding of how mass might play a role. So we follow the similar line of logic that we did before. The net force on the moons will be proportional to the force of gravity from the planet closest to the moon. There are other forces, but they're going to be so small and canceling out with each other that really the only force of consequence will be the force from the planet pulling the moon in orbit around it. The force of gravity from that planet is proportional to the moon's mass times its centripetal acceleration. So again, by looking at the centripetal acceleration of the moons and the number of moons that orbit the planet, we can come up with some sort of idea on how the size or mass of the planet affects the gravitational pull on the moon. And Newton realizes that there looks like there is a proportional relationship, where if I have a planet that is 10 times more massive than another planet, it would create 10 times more gravitational force at the same distance than the smaller planet. So Newton was able to then derive that the centripetal acceleration of a satellite something that orbits something else, such as the satellite that we have right over here. Its centripetal acceleration would be proportional to the mass of the thing that's pulling it into the orbit, such as the Earth, divided by the distance of separation, or the radius of the orbit, squared. And since net force is the mass of the object, that would be the satellite, times its personal acceleration, then the force of gravity on the satellite should be proportional to the product of the masses of both the satellite and the planet divided by their distance of separation squared. Basically, all we're doing is we're taking the statement that we have for acceleration and substituting that in. But this is not an equation, it's a proportionality. Now, to make a proportionality into equation, you really only need one other thing to be added into the statement, and that is a multiplying constant. So the force of gravity between two objects is equal to some constant times the product of their two masses being multiplied together, all divided by their distance apart squared. Newton had only one small problem. He was able to come up with an equation, and he called that constant the letter g, and he was able to say that the force of gravity would then be equal to g, m of the first object, m1, times mass of the second object, m2, divided by the radius squared, but he didn't know what g is. He was able to apply his third law of motion and say whatever force of gravity m1 feels from m2 would be equal in magnitude, just opposite in direction, of whatever m2 feels from m1. The forces would be equal in magnitude, just opposite in directions. We really can't turn around and say that to the right is positive or to the left is negative, because that would be all very arbitrary. So a lot of times when we're dealing with gravitational forces, you might see in a vector equation that has a negative sign in front of it. This is using the radius as a positive direction. So as far as m1 is concerned, anything going away from m1 would be a positive direction. So the force on m2 would be a negative direction because it's pulling towards m1, which would be against its radius. And likewise, from m2's perspective, its radius would be going towards m1. So if m1 is being pulled towards m2, that force is against m2's radius. So from m2's perspective, that force is also a negative. Some people find this very confusing because, according to Newton's third law, if my two forces are going to cancel out, they should be opposite signs. And that typically is true, especially if working with a Cartesian coordinate system. But this one isn't. This is a whole other coordinate system based off of a polar coordinate system. So it doesn't really apply here. However, we're often going to be working with just the scalar equation because we're only interested in the magnitudes, and the picture often allows us to determine what direction the forces are pulling. So often you'll just see the absolute value of Fg equals g m1 m2 over r squared. It is important to note that sometimes you will not see the absolute value signs in the equation. They'll just simply not bold the f to show that it is a scalar instead of a vector.